Hello dear students, today we are going to have a discussion on surface plasmon resonance, which is an important concept in nanochemistry as well as in various sensing applications and all. So we already said that as you go to the nano range, you will be having different properties for different materials. Most of the materials will be showing this, and most pronounced this kind of change is observed in the case of metallic nanoparticles and semiconductor nanoparticles. So the surface plasmon resonance is mainly focusing on the properties of metallic nanoparticles and why these properties will be arising. So a simple example is if you are taking a bulk gold material like a bangle or something that you have, it will be having a shiny appearance like this. It will be having a golden color like this. But if you are taking this particular material or this particular thing and making this to a nano level, you're cutting this to a small piece and ultimately reaching to a nano material. You won't be observing this kind of golden or shiny appearance. Instead of that, you will be seeing colloidal material like materials having size in the range of 10 to 100 or 120 nanometers, which is having peculiar colors like golden, wine red color, purple color, etc. So this particular property, this particular way we see this particular compound will be entirely changing as you move from this bulk material to nanomaterial. So we are going to talk why this change occurs and the reason behind this particular change, and that can be explained using surface plasmon resonance. So as we already mentioned in our last class, surface plasmon resonance is a collective oscillation of conduction band electrons that are in resonance with oscillating electric field of incident light, which will produce energetic plasmon electrons through non-radiative excitation. So you have conduction band electrons which oscillates, and these oscillating electrons can interact with the electric field of the electromagnetic light that is falling on it, and this will produce energetic plasmonic electrons through non-radiative excitation. So the important thing you have to remember in surface plasmon resonance is there is oscillating electrons which are in the conduction band, and they will be interacting with the incident light, the electromagnetic component of the incident light. So let's consider a metal. You may have studied the bonding in metal, how the electrons are arranged in metal, and in different compounds or different types of bonds there will be different kinds of arrangements of electrons between the atoms of concerned atoms. If it is a covalent bond, it will be very much localized. If it is an electrostatic bond or ionic bond, there will be the electrons will be transferred to one atom, and there will be electrostatic attraction between the ions that are formed. In the case of metallic bond, what happens is that you will be having the metal ions which is having positive charge, and the valence electrons, so the electrons that are taking part in the chemical bond, will be loosely arranged around the metal ion. So here you can see in the figure there is a a system containing large number of positive ions, and there are electrons, and these electrons will be loosely present in that particular system. So in a metal, if you're considering this as a metal, you have gold ions, and the particular electrons that are taking part in chemical bond, that is metallic bond, will be present all over this particular metallic surface or metallic all over this metal. So you cannot say this electron is present here. It will be moving in that particular conductor. So we cannot say this an electron as a particular particle. This electron would be present near this. We cannot say like that. We cannot say this electron was donated by atom number 1 and this electron is present near atom number 1 itself. Cannot say that in the case of a metallic bond. Instead, in a metallic bond, there will be electrons which are delocalized along the conductor. So there is a sea of electrons in the conductor. That is the term that we use in the case of metals, metallic conductors. That is, the metal will be the electrons that are taking part in the chemical bond will be delocalized along the conductor. If it is having the length like this, if the electron was donated by even by this metal, this electron can move all along this particular conductor. So the electron donated by a metal in a conductor is not the property of that metal after that metal atom after that particular instance, after formation of the bond. It belongs to the conductor and it will be behaving as a single entity or single particle or something. So all these electrons in this particular metal will be this member of a single quantum state. You have to look into different books to understand the terms in depth, like quantum states, plasmon, quasi-particle, etc. We'll be just mentioning these terms to understand what happens during the surface plasmon resonance. So the electrons that are taking part in chemical bond formation in the case of a metal, that is for the formation of a metallic bond, will be having a collective nature and they will be the member of a same quantum state and they will be undergoing oscillations, periodic oscillations and all. And all these electrons, if there are 100 electrons or million electrons, all these conducting electrons will be behaving as a single particle. And this particular particle whose vibrations or the oscillations are quantized, when these oscillations are quantized, we term them as plasmons. So in a conductor you have a sea of electrons which are in a quantum state and which can behave as a quasi-particle, and when the vibrations of this electron, they will be interacting with the external stimuli. Whenever you apply an external stimuli, they can interact with the external stimuli, but they will be interacting as a single particle, as a particular quantum state, or as a quasi-particle. Quasi-particle is something that can behave as a particle, and for convenience we will be treating them as a single particle itself, but they are not actually a single particle. They will be a collection of particles. So the plasma oscillations of electron density in a conducting media such as plasma oscillations are the rapid oscillations in a conducting media. So when these plasma oscillations are quantized, we say plasma oscillation of this quasi-particle is quantized, we say that is a plasmon. So we have different terms in terms of this surface plasmon resonance. The first thing is the sea of electron. The second thing is the electrons. All these electrons will be in a single quantum state and they will be oscillating, and the plasma oscillation is the rapid oscillations of electron density in a conducting media, and we have all these electrons to be considered as a quasi-particle, and when these oscillations of the quasi-particle is quantized, we say that is a plasmon. So these plasmons we observe in the surface and they are termed as surface plasmons. And coming to the next thing, we see when we look into the metal, we can see they have a shiny appearance. This is due to the surface plasmons. So when light falls on this particular metal surface, there will be some kind of phenomena and interaction with the plasmons and the electromagnetic component of the light. So we have to know, in the case of light, there is electric component as well as magnetic component, and the electric component will be that which interacts with the surface plasmons and giving this kind of giving this kind of changes. So when a metal surface is irradiated with a light, the electric component of the light will be interacting with the plasmon, that is oscillating magnetic field of the electrons. And what happens? What happens is that this oscillating electronic field, and the electromagnetic field will make the electrons or electronic oscillation to move in a particular mode. The electromagnetic field of the light would make the surface plasmon to interact with it, and it will be changing the mode by which it was present in the earlier stage. So prior to the incidence of the light, there was some kind of movement, some kind of vibration and all for that particular surface plasmon. Upon the incidence of the light is incident on the material surface, the surface plasmons will be interacting with the electromagnetic component of the light, and it will be changing some properties or some modes of vibrations or some movements of that particular plasmon. And this change will generate electric field in that particular material. And this field generated will be the field that generated on the surface of the metal will then oppose the incident electromagnetic light, light, and some energy would be dissipated throughout the surface of the metal, and some energy would be absorbed by the particular electrons or surface plasmons, which would be re-emitted back. And this re-emitted back light or re-emitted back energy is termed as the glazing that you observe for the particular metal conductor. So all this shiny appearance is occurring when you irradiate this particular metal surface with suitable light. So this surface plasmon can interact with a wide range of wavelengths, and when you irradiate this surface with a light, the electromagnetic component of the light will interact with the surface plasmons, and there will be considerable change in the energy distribution, and the production, some electric field will be generated within the conductor, which will oppose the electromagnetic rays, and the electric component of the rays would be opposed, and some energy would be dissipated along the surface, and some energy that have been absorbed by the plasmons will be reflected back, and it is observed as the glazing of the metal. So in the case of nanoparticles, the scenario is very different, because in the case of nanoparticle, we are considering particles having size in the range of 0 to 100 nanometers. So that is very low size. If you are considering the size of this material, this bangle, and the size of the nanoparticle, gold nanoparticle or silver nanoparticle, the size of nanoparticle is very low. The light that you are using is in the range of 400 nanometer to 600 nanometer in the visible range. Visible range light will be having wavelengths in the range of 400 to 600 nanometer, but the size of our particle is very small. So there won't be the theory that we said earlier for a bulk material cannot be easily applicable for this particular nanomaterials. Here we say there is localized surface plasmon resonance. That is an advanced term that you don't have to worry about. And here what happens is that here in every nanoparticles you will be having plasmon associated with them, and this plasmon will be oscillating, and when you irradiate this plasmon or this nanoparticle with suitable light, there will be at some point the frequency of oscillation of the plasmons of the nanoparticle will be equal to the frequency of electromagnetic radiation, the vibrations. So at this point, at this wavelength where the frequency where the oscillation of the surface plasmon is equal to the oscillation of the light, there will be resonance. And only at this frequency or only at this wavelength there will be strong absorption for a nanomaterial. So if you look at gold nanoparticle, you can see red color because it will be absorbing at some around 400 nanometers or 500 nanometers. In the case of gold also, silver also, you can see a yellowish color. It will be absorbing in the range of 500 something, and this is due to the fact that the surface plasmons will be having an oscillation in this particular frequency region, and the electromagnetic rays can interact with the nanoparticles, and there will be resonance only at that particular region. So if we are increasing or decreasing the frequency of radiation, there won't be much effective resonance. So if you are plotting a graph of the absorption, you can see a graph of wavelength versus absorption. You can see for nanoparticle there will be a peak only at a particular wavelength. That is because only at that particular wavelength there is maximum resonance. So in case of nanoparticle, the small size will be causing this kind of interaction or resonance, and this is the reason for the color of nanoparticles, metal nanoparticles. So here you can see the color of various gold nanoparticle. As you have a 20 nanometer particle, it will be having a red color, and as you move, you will be having 60 nanometer particle which is having a blue color. So the absorption has considerably shifted from red to from this region to this region. So this particular property is associated with the size of the nanomaterial. As the size changed, the resonance frequency become different, and hence the frequency at which the light was absorbed become different, and so the color we see is different. So this is a spherical nanoparticle. If you are taking a nano rod, the color would be different. So in the case of nano rods, you can have different colors like this depending on the size. So depending on the size, you can see it is blue, green, black, red, etc. So the surface plasmons resonance will be depending on both the size as well as the shape of nanoparticle. So if you are able to manipulate the reaction in such a way that you can create nanorods, spherical nanoparticles or nano cages, etc. You can have a wide variety of materials which is having different shapes, and when you are having different shaped particles, that is in the case of nanorods and all, the surface plasmon behavior would be very much different than that of this spherical nanoparticle. That you can read you can study in higher classes, but this is a very interesting field and very widely used in many applications. And here you can see as the size of the nanoparticle is changing, the color will also be changing. This is a TEM image showing how the size varies, and here in this picture you can see the color of the nanoparticle, and also the aspect ratio as it changes for gold nanorods, the color of the particle will be changing. So we have discussed so far what surface plasmon is and what surface plasmon resonance is, and how this is significant in the case of nanoparticle. So the basic thing you have to remember is what surface plasmon is. It is a collective oscillation of conduction band electrons that are in resonance with oscillation of the electric field of light. So conduction band electrons are involved in this particular phenomena, and in the case of nanoparticle, due to that particular size of nanoparticle, this particular color change is observed. So I think it is clear, and try to read more about this particular topic from internet or from books, because it is very interesting and very useful in various applications like antibody antigen sensing, studying the interaction between various proteins and drugs and all. You can use this kind of surface plasmon resonance techniques. So thank you.